All right, guys, I'm so excited. I hope you guys are excited. This is going to be great. So, like I said, I'll just one more time. There's just a few things. Read the box, heed the box, right? There's what it says in that box at the very beginning. There are diagnostic tests A, B, C, and D. Like when I had that open, I just glanced at it, and that looks like, you know, that first page looks like one assignment. And you think, yeah, that's about right. 10 questions. It's like a homework assignment. This is much longer. That's why I'm giving you to next Tuesday to have it done. You will have homework on Thursday. So I suggest you try to knock as much of this stuff out as possible. Also, that way you're not playing catch up. You don't want to because we're going to go into new material Thursday. And you don't want to be learning new material as you're trying to review old stuff and seeing where your stuff is. So I would suggest that you do as much of this as possible. And if you want to turn it in Thursday, that would be cool. I will accept it Thursday if you want to turn it in. Otherwise, it's due Tuesday. That's next week. Okay, here we go. So, we're going to use the power of imagination. We're going to imagine that you both are driving in a car. You're driving in the same car, okay? And Noah, since you're on that side, Noah, you're driving. Victor, you're not driving, okay? And you're driving, you're driving, you just get on the highway, right? And you hit the cruise control. And we're going, cruise control, right? It's supposed to keep you at the same speed, right? But in reality, the wind blows, it slows you down, and so you slow a little bit, and then it speeds you up, and you go past it, and you slow down, and you're just constantly moving up and slowing down. We're going to pretend that this is a perfect speed control, or cruise control, and you're going exactly one constant speed the whole time, okay? So this isn't real. This isn't real life, but this is what we're going to pretend. So you're driving on the highway. And Noah, what you do is once you get up to speed, you set the cruise control, you see a mile marker coming. You know what mile markers are, right? They're the little line, they're on the side of the highway, and it has a little number, right? And it says like mile, say 120, right? And so you notice and what you do is the instant that you pass mile marker 120, you start a stopwatch, okay? So you're at time 0 the instant that you go by 120. I'm going to go ahead and say you shouldn't have done this. When you're driving, you need to be paying attention, but we'll forgive you. We'll forgive you for the time being, okay? So this is the experiment you're running. And what you do also, which you shouldn't be doing, Noah, is you keep track of this, okay? Like, I don't know, maybe you use like a voice command or something on your phone and you record it, right? But you note that at time 0, you are at mile marker 120. Okay, and so you make note of that. And maybe you have it as like a table or something like that, right? Like you have your mile and you have your times, right? And so you have 0, mile marker 120. Okay. Exactly 1 hour goes by. Exactly 1 hour goes by. And you note that, oh, here comes a sign. And so exactly 1 hour has gone by. And you note that you're at mile marker 180. 180. Okay, so you have 1 and 180. Okay. And so on and so forth. You notice that after exactly 2 hours have gone by, you are at mile marker 240. And this is what you're writing down, which you shouldn't have been doing while you're driving. You should not be writing things down when you're driving. Victor should have been doing this, but he's doing something else, which I'll tell you about in just a minute. So finally, 3 hours go by. Exactly when your clock goes exactly at 3 hours, you exactly go by the 300. Yes, yeah, okay. So you guys, you're kind of seeing what's going on here, right? Yeah, you get this. And so later on, you come back. That's the end of your experiment. Maybe you get off the highway there or whatever. I haven't thought that far into the future. But now you have this data. And what you decide to do is you're going to graph this data, okay? And so you have, here at time 0, you have 120. So you're like, okay, there's 120. Here at time 1, let me try to do this, 2 and 3. At time 1, you have 180. let's make it that high right there. That would look good, huh? 180 here at 1. At time 2, you have 240. So you're here at 240. There. And at 3, you have 300. Okay? Now, you know that because you have this perfect cruise control in your perfect car, you know that you didn't slow down, you didn't speed up or anything like that. And from that you can infer that the graph, if you were to graph this thing, it's not going to be jumping around like that, right? It's not going to, or like stay like this and then all magically come up there. Because that would mean, if that were to happen, that would mean like you stopped at mile marker 240 and then took off really fast to get up to 300, That didn't happen. In fact, if you were taking more samples, if instead of doing this once every hour, you were doing it every 30 minutes, you could infer reasonably that you would be exactly halfway between these guys, right here and here and here, right? Yeah. Right? It certainly wouldn't jump up because you didn't go past 180 and then reverse on the highway and come back, right? And so on and so forth. If you took a sample every 15 minutes, you would have all of these, and et cetera, et cetera. And if you somehow could monitor continuously, maybe you have a computer system in your car that does this, right? You would have some object. What do we call this type of object?
A line.
A line, right? Yeah, and indeed, if your speed is constant, if your speed is not changing, I'm just going to state this now, but we will be able to prove this soon with calculus. If your rate of change is constant, which we've assumed it was, which of course doesn't happen in the real world, but we've assumed it's constant, then your record of what happened is a line. It's a straight line, okay? Now, here's a few questions I want to get out of the way here. So, this is a function, yeah?
Yeah.
Right? There's an input-output relationship. I could give you any time. You could plug that in and find out where you were. So, time is the input. And time is in units of what? Hours. Okay. And now, what's my output? Miles, right? My output is in units of miles. Okay, so we're all on the same page there. First question. How fast are you going?
60 miles.
How did you figure that out?
Well, I'm going to go 180 minus 120.
So in other words, you're telling me that this distance here, right, is what? You said it's 180 minus, so let's write this out. 180 minus 120. That gives you what?
60.
60. And then what did you do to get your per what?
The run is...
And the run is what? How much?
1.
1. And you got that by taking this number and minus, well, actually you probably didn't. You just said, look at it's 1. That is 1 right there. And you're right. And so you said, okay, that's the same thing as 60 over 1, which is 60 miles per hour, right? 60. And now, does that make sense units-wise?
Yeah.
Right? Because you took, that was a measure of miles, so you have miles on the top. That's a measure of hours, and so you have hours on the bottom, and so you have miles per hour is your new unit, I guess, when you divide those things by each other. Now, there's 4 points here. To calculate a slope, you need 2 of them, so that's 4, choose 2. So that's 6 different ways of doing this. You could have done that here. You could have done it here. So that's 1, 2, 3. You could do it with these 2, 4. You could have done it with these 2, 5. You could have done it with these 2 to give you 6. And you'd get the exact same thing every single time. Because we've assumed this is a line. The slope isn't changing. It doesn't matter what 2 points you take. Like for instance, which ones did I do? I took, you could go from, you could do the whole thing, right? You say from here to here, that would be 300 minus 120, right? Right, that's that total distance from 300 minus 120. And then over the run here would be, that looks terrible. 3, there we go. 3 minus 0, which would be 180 over 3, which lo and behold is still 60, right? Because this whole time we've assumed something that's really functionally impossible in the world is that your speed was constant this whole time. And we've just kind of discovered that your speed is the slope of this, right?
Yeah.
Okay. And the units match up when you do that. Okay, so second question. How far did you travel during this experiment?
300 minus 120.
Yeah, that's how I would do it, right? Like, it's this distance right here, right? Like, and this is why I drew this right here, is because if you started off on your experiment, and like, you could actually see, like, literally, well, that's what we're talking about, is this distance. We're talking about the number of miles between mile marker 120 and mile marker 300, which is the same thing as you take your final position, you minus off your initial position, and you get, what is that? What's 300 minus 120?
180.
180. So this is, what was your speed? And this is your total distance. We said that you take your final minus off your initial to get, what did we say it was again?
180.
180. Thank you. Okay, miles. And that makes sense because you take a number of miles, you subtract off a number of miles, and you get miles. You're not going to get sandwiches. You're not going to get grams. That makes perfect sense. Okay. Another thing we want to do. I want a function. Find a function. Let's figure out a function and what I want is that where I input time in hours, and it gives me my position in miles.
F of t.
Okay, yes, that's exactly what I was going to call it. That's what's in my notes. F of t equals, now let's not try to get this all in one fell swoop. What should this thing look like?
A line.
So
MT
plus B. Okay? Right? That's because we know this is a line. We haven't proved that. We will prove that soon, that a constant rate of change gives you a line. It is true that when you have a constant rate, which was the assumption at the very beginning, that you get a line. And so you could just go ahead and say, well, this function is a line. Therefore, it has this form. The only things that remain are finding m and finding b. How do I find m? We already did it. And there's 6 different ways to do it with this, but yes, we already have it. And so we know that this is 60t plus 1. In this case, it's easy because we have we have a y-intercept. So it's super easy to find that. But let's say we didn't. Let's say for whatever reason we didn't have that data point. Let's say that we only had the one where the input was 2 and the output was 240. We would know, because we have the slope, that it's 60t plus b. But how would we find b if we only had this one data point here?
Plug in a 0.
Plug in a 0, okay.
For t.
Plug in a 0 and it gives you 60 times 0 plus b equals, we don't know because I'm assuming that we don't know what that is.
Oh, plug in a point you already know.
Plug in the point that you know, okay? This is going to be super important, right? For this class. You plug in the point you know. So what point what's my endpoint?
It's 300.
We could do that. Okay, that's a no. I was saying if we only had that one.
Oh, okay. Oh.
But it doesn't matter. Let's say you told me plug in 3, get out 300. Okay, we plug in 3, get out 300. F of t, so I plug in 3, I get 60 times 3 plus b equals 300. What's 60 times 3? 180 plus b equals 300. So that b equals whatever 300 minus 180 is. I'm betting it's 120 because everything's consistent here, right? Okay, and so we could have done that a couple different ways, right? We had an obvious one because we knew what the intercept is. We know what it, when you plug in a 0, you got to get out of 120. So that's what we're getting there. But if we didn't have that, we could have done some shenanigans to figure out what we were looking for. Okay, nice. So again, from this, we could figure out the speed. We could figure out the total distance traveled, and we could get a function, which then we could ask a question like, what mile marker were we at say 1.5 hours? Well, how would you find that out, given this? What would you do if you wanted to know what mile marker did you pass at one?
Plug in 1.5 hours.
Plug in a 1.5 and it'll tell you where you were, right? That's the whole idea of a function. That's what's so nice about a function, is basically this tells you everything you could possibly want to know about your trip. You want to know where you were at 2.5, you just plug in a 2.5 and out will pop where you were at that time, right? That's one of the really nice things about a function. Okay, all right. Okay, while Noah was doing this, Victor was doing a similar thing, only instead of keeping track of where he was, all Victor was doing was just looking at the speedometer. And every time that Noah took a reading, right, he took one at 0 hours, at 1 hour, at 2 hours, and 3 hours, Victor looked at the speedometer and kept a record. So we have time and we have speed. And so when you started the experiment, what did Victor record? 60, right? At 1 hour, what did Victor looked at the speedometer and saw that it was at 60, right? This should not be magical to you. Like, right? Like this, right? Okay, when it was 2, Victor looked and saw that it was 60?
Yeah.
Yeah, okay, still 60. And then at 3, because we're assuming it was constant the whole time, it was still at 60. So what Victor does is gets home, or you guys get off and you go to a coffee shop or whatever, and you guys get off the highway, go to a coffee shop, and what Victor does is he plots his data. Now, time is in units of what?
Hours. Yeah.
And what's the output here?
Speed in miles per hour.
There you go. He's doing speed in miles per hour. Okay, so when the input was 0, the output was 60. When the input was 1, the output was 60. The input was 2, the output stayed 60. When the input was 3, the output was 60. And then, of course, Victor uses his giant brain and his superb reasoning skills to say, you know, I don't remember the speedometer ever changing. We didn't pop up and pop back down. It just stayed at 60 the whole time. So he says, you know what? This is a really good assumption here, to just say it was 60 the entire time. Okay, so that's what happens. So here's the question.
You could still figure out.
Can we figure out how fast you were going?
No. 60.
60, right? You were going 60. And how would you do that? Like, just given this data, you'd say, well, there's your speed. That's your speed is the output. And I could have asked you at any time. I didn't do this over here. I said how fast you were going because it was constant. But I could have asked, how fast were you going at time equals 1? And you'd say, well, it was the same the whole time. I could do the same thing here, right? I could say, how fast were you going at exactly 1 hour? And you would say
60.
And what you would do is you'd say, okay, it was 60 miles per hour the whole time. Now, you guys haven't looked at each other's notes yet. Victor, you were not looking at the mile markers. Okay. You have no clue what the mile markers were. You were just focused like a hawk at the speedometer the whole time.
Yeah.
Now, Noah goes to the bathroom, and I come in and say, how far did you guys go?
Well, if it was 3 hours at 60, then it'd be 180 miles.
What calculation would you do? you would say, well, I was going 60 miles per hour. I did that for 3 hours. And you told me that 60 times 3 was what?
180.
180. Now let's look at the units on that and make sure that you're not just jumbling numbers around. Let's see if this makes any sense. 60 watts?
Miles per hour.
Miles per hour. Times 3 what's?
Hours.
The
hours cancels miles.
The hours cancel out and you get
mile.
So indeed, yeah, okay, this works. This works. That's how Victor would have answered this question, because he had no idea what mile markers were passing, but he could still get the exact same information. Okay? Okay. Now just for symmetry here.
Let's make a function.
What's a function? Give me a function for this. First off, what type of object is this? It's a line, and so it has the form what?
F plus B.
Let's call it g of t equals
60.
Yes.
60
but in general, it would be mt plus b. And you'd ask yourself first, well, let's get the slope out of the way. What's the slope of that line?
0.
It's 0. Okay, so
it's just 120.
It's just...
No, 60.
It's just 60. It's always 60, right? And so I'm going to get rid of the mt plus b part, right? Yes, you're right. It's just 60. No matter what the input is, the output, at least in your domain, we don't have any record of what happened before. And so it's not in our domain. We can't just plug in a -1 because you weren't recording anything. It doesn't make sense to ask that question. You can't say, what about if I plug in a 4? Well, you weren't driving then. You were at the coffee shop because you guys take forever in the coffee shop, right? And so you were there for over an hour. And so I guess you could say your speed was 0. But you know what I'm saying, right? Like we only have a record of this right here. So, but you plug in anything in your domain and you could say like, so for instance, when I asked, how fast were you going at time equals 1, you would say, well, that's the same thing as g of 1. I plug in my 1, I get out a 60, right?
Yeah. And
so now let's think about this in terms of functions real quick. Make sure there's not anything else I wanted to say here. There is something else I wanted to say. My point with like putting these two things together, one of my points, is that all of the information right here, all of the information of f, this is f of t, this is g of t, all of this information, every single bit of it is contained right here, except for one bit. One point, where did you start, right? Yeah. And as we already talked about, even if we don't know where we start, we could still figure this out, right? Like I said, pretend that we didn't know this, but we knew this point. Or if we knew this point, you could still get all of that back, right? Just like we did. We plugged in a 3, got out a 300, and then solved and found, oh, it's 120. All of that information, everything except for one point, you give me any one point there, if I knew where you were at any point along that line, all I would need is this information. And I could exactly reconstruct this right here.
Well, you wouldn't, you wouldn't know how many, like what mile marker you were at, but you would know how.
Right, and that's what I mean. Oh, it's the only thing that's missing is where did you start, or where were you at any given time, right? But you would know, like just given this, if you said, okay, I know that you were going 60 miles per hour from time 0 to 3. So in general, that would look something like this. The only question is, where did you go through right here, right? Because, so you guys see what I'm saying here? Like, the only, you know that the function would look exactly like this. Because you were going 60 miles per hour, and so you must have been going north. That's the only thing it could be. The only thing that remains to be found is where did you start. So, having a record of the speed gives you everything you need to know about the original trip. Except for one point. But ultimately, it's just like, well, where were you? This is what the picture is going to look like. We're only going to shift it up or down, basically. It has to look like this. Another way of saying that is, this tells you the slope is 60. Always. That's what a slope of 60 looks like. The only question is, well, what's the shift? You know, shifting up or down. Okay? Okay. Everybody Everybody get any questions on that so far? No? Okay. Now we're gonna make this. Let me just make sure. Hold on. 60. Knowing that marker. Yep. So all of that. Okay. Okay. I'm gonna get rid of all this stuff. Am I gonna get rid of all this stuff? Even the homework. Okay. Here we go. Now let's be a little bit more, slightly more abstract. And I'm deliberately doing. This is just our introduction to calculus. Okay, like I'm giving you a 5,000 foot picture of what we're going to do in this class. I'm doing it with a specific example. We're going to get into how to do what this is all about in general as we move on. But I wanted to start with a specific example because, interestingly, you guys knew exactly what I was talking about. You even anticipated what I was about to say. You're like, you're going 60. Well, yeah, right? And so, okay, I just want to bring something up. The question, how far did you go? Another way of saying that is, what is your displacement? Because it would be different if you went north for a ways and then stopped and came back and then went here, you know what I'm saying? Yeah. Like if you went up to 240, then you came back down to 180, and then you went up to 300. How far did you travel? Well, that would be different because we'd have to keep track of coming back and stuff like that. So just bear with me here. How far did you go? What we're talking about here is displacement. Like your final bit minus your initial bit. Like that in the end, your actual trip notwithstanding, like you started at some point, you ended at another point. What's the displacement there? How far were you displaced from beginning and end? So that we found on one hand. Actually, let's just real quick. I'll go ahead and do that. So over here, how did we do that? We said, well, you take your final place, right? Remember, f of 3 is the output you get. So that means 300, right? We take your final position and you subtract off your initial position. That's how we did it, right? And it's right there, 300 minus 120. That's what that means right there. But we said, that's the exact same thing, we noticed, as taking the value of this thing, g of t, because it happened to be the same the whole time, and multiplying it by the total time that we had here, right? Times, in our case, 3 hours minus 0 hours was a total of 3 hours, right? Everybody got that? Now, graphically, what is this on this graph?
It's the same thing, but wait.
You took the height. This is g of t.
Same as the slope on the other one.
Yeah, but what I'm getting at, like I see what you're saying, but what I'm getting at is that is the area, right? You take the height, multiply by the width. That's how you got it. And it turned out that the units actually matched up too. The height was in units of miles per hour. The width or base was in units of hours. Those canceled out to give you miles, which is what the output of this thing was. Okay. How did I want to do this? So a little bit more generally, we can imagine if we started at any other time and ended up at any other time, what we would have here would be whatever time it was, your final time, that's what t sub f is going to be, okay? Your time final minus your initial time, times 0. And that would be the same as, now instead of, it's still whatever the output of this thing was, and now just whatever the change in time is, which I guess would be t final minus t initial. And in our class, we're going to have a special way of writing that. Delta t. Okay? So if I have some x final minus x initial, we're just going to call that delta x. Delta means the change in. Okay, so when you read that, you could read that as either delta x, that's how we're going to say it. But what your mind should be thinking is the change in x. So the change in the x value, the change in the t value. So you take your, whatever your output is, multiply it by the change, and that gives you that. Okay? And indeed, like what happened here was you took, it all worked out units-wise. We took miles minus miles, and we got the same thing as when we took miles per hour times hours. There's nothing new here. And in fact, I remember in Algebra 2 giving you problems like this. There were a bunch of homework problems like this, right? And sometimes there's stuff that was hidden and everything, and the question was how fast were you going? Sometimes you had info like this, and it was like how far did you go, you know? All that information is connected. It's all there. And when you're dealing with lines, okay? I think I actually wrote down what I wanted to say here. Yeah. As long as your speed or whatever function you're talking about, as long as it changes at a constant rate, the rate of change is constant, then we don't need any tools bigger than Algebra 2. The stuff we learned in Algebra 2 is completely sufficient to answer any of the questions you could possibly ask about this. And indeed, the ultimate question is, can you give me a function which describes this? Because then there's no question you could possibly ask me that I couldn't give you an answer for, right? And so Algebra 2 is enough to do that. But in the real world, speed is rarely ever constant. And if it is constant, it's like for a brief period of time, right? And so while all of that stuff is great, like we could analyze stuff generally like that, it's less realistic, and like this won't work so well in the real world, okay? So let's do a slightly more realistic thought experiment here. You guys ready for this?
Yes.
All right, I'm going to get rid of this stuff. Slightly more realistic. Going to be something like this. It's a highway. Still a highway. Now we have an off-ramp, or an on-ramp, I'm sorry. There's an on-ramp here. And have you guys seen on-ramps that are metered? Like there's a stoplight
Yes.
right here, right? Okay. So like you come off, you go to get on the highway and there's a stoplight and you have to stop at the stoplight. So that's what we're imagining we're doing. Noah's driving again. He's waiting at the stoplight. This stoplight happens to be, I'm going to run out of room if I do it this way. I'm sorry, guys. Boy, this is... Look at that. Okay, so here's the stoplight. Here's a car. This car happens to be exactly at mile marker 120. Okay, so like, you're sitting there in the car. You look over and you see, oh, mile marker 120. It's right there. Ooh, I'm going to do another experiment. And so what you do is you start your clock the instant that the light turns green. And at that instant that the light turns green, you take your foot off the brake and you start to go. Okay? So the light turns green and you accelerate at a constant rate. Okay, now we're talking like you're going to be speeding up, but you're not going to start speeding up and then like kind of slow down like you actually would in the real world because there's cars coming and you start to speed and you go, oh, whoa, whoa, I got to wait for that guy. Oh, I got to get ahead of this guy, you know. We're just going to assume, and we're going to assume you have a perfect car, which you push the gas down and it moves and it accelerates at a constant rate, okay? So you're speeding up, but you're speeding up by the same amount every time. Does everybody get that?
Yes.
Okay? Okay. So that's the brain exercise that we're doing. Okay? You're going to accelerate until you get to 60 miles per hour and then set your cruise control at exactly 60. Okay? And let's say, just to make calculations easy, that it takes 2 hours for you to accelerate to 60. Right? So your car is about as good as my first car, right? And it takes you about that amount of time, right? But the point here is I want to think, and the reason I'm doing this is just so it'll be easy to draw and it'll make some future calculations much easier. So what this is going to look like initially, like the instant that that happens, your speed is 0. And you can imagine what a speed of 0 would look like, right? Like if your speed were 0 and you didn't move at all, well, you wouldn't move. It would just look like this, right?
Yes.
Like you didn't instantaneously start going like 60 miles per hour so that you jump off like this. That's not what it would look like in the real world. In the real world, you're going to start slow and then start to speed up as you go along. Okay? And so what this is going to look like, I'm going to exaggerate this. Something like that. It's going to be a curve, right? You start off going slow, and you start to go faster and faster as time goes on. Like initially, it took you a whole hour to get this far, right? But then over the course of the next hour, you actually go farther, right? So initially, I'm going to try this a little bit better here. Something like that, right? It took you, because you're accelerating, you're going faster every time, it took you an hour to make it to here, right? And so you covered this many miles on the highway. But now over the course of the next hour, you're covering more miles because you're going faster the whole time, right? So everybody can read that and see, like, that's what I'm saying here, right?
Yeah.
But now from 2 to 3,
The constant.
it's gonna look like a straight line, right? And you're not really changing your speed. It's not going to like give you a bend in the graph or anything like that. You're not going to magically just jump up real fast. It's going to be this nice smooth connection, and I can't really draw it very well. I'm going to try, but it should look like this. Like if you imagine, you know, like you're going along, and I'm kind of thinking about the slope at this point, right? Like it would do this and do this and do this until whatever this is, now that you've hit 60, it's just going to continue on like this, right? You got that? And because I did this the way I do, I'm just going to pretend like that, okay? It's terrible, but I think you get the idea, right? Your speed was changing until you got to the point where your speed no longer changed, and now you're going in a straight line, okay? Remember, this is not the direction you're driving. You're not driving northeast, right? We're just talking about the cars just moving straight north. But we're keeping a record of the time, okay? And Noah does the same thing. He keeps a record. Just like that. We drive for 3 total hours, okay? It's going to look something like that. Here's the question. How fast are you going at 1 hour?
Half of 60, so 30. If you're accelerated constantly.
Yeah.
I think you're right about that. Okay, and that's a very, and we will analyze that in just a minute. Okay, but here's the thing, that's not the data that your car has picked up on, right? And another thing, I don't think I said this. We're going to assume this time that your car, we would not be able to figure this out with only these. Like, you didn't know, like, your speed record is non-existent. You aren't keeping track of speed. You don't know that at time 2 you went straight, or that you set the cruise control. I don't know how you didn't know that you didn't set cruise control. Let's say you forgot, okay? You forgot when you set cruise control. You just know that you set cruise control, okay? But yes, you're right, and we'll see in a minute, graphically, we'll figure all that out. But like, when you get back, what you have now, instead of actually writing this down, you have a computer that's keeping track in your car of every one of these points. Maybe it takes a sample every millisecond, we'll say, right? And so your data, when you get to the coffee shop and pull out your laptop and upload all your stuff, you look at it and you just have a bunch of points right here. That's all you have. You have points here, you have the times here, and the outputs here. Okay? You want to know how fast you're going right there. What do you do? Yeah, that would be nice, but that's the computer didn't spit that out. It just gave you a bunch of points. What would you do to estimate your speed right there? Any ideas?
Take the slope in between two of the ones that are right next to each other.
Ooh, that's good. That's good. So we want this one. So what are we going to do? We want the slope where? Which ones?
Between the two like the millisecond at one and the millisecond right after one.
So the millisecond before it and after it? Is that what you're saying? Or the one that we care about and the one right after?
Yeah.
Okay. So that is one way we could do it, and that would be a very good way. And if that's the only data that you had, you would say, you know what? It's probably going to be a good idea to just take those 2 points, find the slope of that line right there. In other words, you wouldn't want to use this one and this one, right?
Yeah.
Like, you could see that's not right. You wouldn't want to use this one and the last one because, well, like, it's not, I mean, you might get lucky, but you can't guarantee. The idea is that the closer you could get these guys together, the more accurate it's going to be.
Yeah.
Right? I mean, that's just kind of intuitive, right? It's still not accurate, though.
Yeah.
In the real world, like that's not exactly what you want to do. And in the real world, if you have a data set like this, what you would actually do is use the point you care about and 2 on the other sides, or 4 on the other sides, and you do something. It's not an average, but it's some, like, you could imagine that if you care about this point and you had this point and this point, one thing you could do is take slope 1, right? We're right there. You could do this one right here and take slope 2. And then you could say that the slope that you care about is like the average of those 2. Right? That's one thing you could do.
Okay.
And in numerical analysis, if that's the only data you had, that is something you could do. It's not exactly the average. It turns out to be a little bit more complicated. You use the center point too, and if you have 5 points like this, you could get it even more accurate, which is cool, and there's ways of doing it. But ultimately, that's not what you care about. That would just be an estimate of the actual slope that you want, which would be the unique line that touches only at that one point that you care about, right? You see what I'm saying there? You have a curve. If you take 2 points on that curve and try to draw a line between those 2 points, it's not exactly what you're looking for. The thing that you're looking for is the thing that touches exactly at one point. And the slope of that line would be, in this case, your speed at that instant.
Yeah.
Does everybody get that?
Yeah.
Right? And you kind of imagine, because if that green curve were a flat line, then they would coincide. And if you were to bend that curve up a little bit, you could see, like, this must be your speed at that time.
But there could be a lot of lines that go through that point, right?
Well, this thing, the blue one that I've drawn, has a special name. Tangent line. You're going to hear this a billion times in this class. The tangent line. And the tangent line is, by definition, given a curve. So we have the green curve there. The tangent line at a point is the unique line that touches that one point and no other part of the curve.
Oh, so there's only one line?
So any given curve, unless that curve happens to be a line, right?
Yeah.
The only way around it is if you have a line, and then you're like, well, what would be tangent to that curve? Well, the line itself, right?
Yeah.
But any other curve, and this curve could be something really funky. It could be something that does something like this and crazy and blah, 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 blah. But now you say, give me any one point on that curve. That one point right there. Well, then there is one and only one line that touches that curve at only one point. See what I'm saying there?
Yes.
And you could imagine, like, if you're keeping a record of your speed as you're doing this, right? This is where you stop. This is where you're going backwards. This is where you stop again. And now this is the point where you're going like that. And you imagine a line right there. That's what we call a tangent line. And what you're trying to do here is the tangent line, in this case where your input is hours and your output is miles, then the slope of that tangent line, the slope of this green guy is miles per hour. It's your speed at that given time. And you can see, like, it's not the same the whole time. Your speed, right? This is what we're saying now. Your speed is changing. You started off, the slope of the tangent line right there was 0 because your speed was 0. And as you start to speed up, the slope of the tangent line increases, right? Until we finally get to where you're going 60, and now the slope just stays 60. Everybody with me on that?
Yeah.
Okay, so here's some spiel. I'm gonna have to read this because I wrote this. Okay. So, like I said, if you're trying to estimate the slope of this line, which is, that's the speed that you want, you're trying to estimate it. In the real world, there are methods where if you have a bunch of points that you could use to take kind of averages and stuff like that to get a good idea of what this thing would have to be. Luckily, we don't care about the real world. We're in a math class. And so what we're going to deal with is not a bunch of points. We're going to assume that we actually do have a function. So right now we're pretending, like you said, you beat me to the punch. It's like, well, if we had a function, like, yeah. And so we're going to assume that Noah's computer, instead of giving a bunch of points, actually spit out a function. And that function, at least from 0 to 2, because we know it's a line from 2 to 3, right? Right? Yeah. Because you're going constant from 2 to 3. But from 0 to 2, it spit out this function. And it told you that it was 15t squared plus 120. Does that make sense? Does this part look like a parabola that...
Yeah, just not...
Right? Because you say 15t squared would look like this, right? It's just a parabola. Plus 120 would shift it up to 120, right? Something like that. And yeah, that's what I drew. I did that on purpose. Okay? Like, that's... Okay? All right, everybody got that?
Yeah.
So we're going to say, okay. Now the question is, now we're not messing around with points. What we actually want is the slope right here, where I plug in a 1. What do I get out of my f when I plug in a 1?
30. Oh, of that. 135.
135. Yes. Uh-oh. Is that right? Yeah, okay.
How does it make?
Yeah, okay. Yes, okay, yes, 135! All right. Now here's the question. Like I said a minute ago, right? If you tried to estimate this guy from here to here, you'd have a really bad estimate. But if you tried to estimate with these 2 points, it would get better. And the closer you get, the better the estimate would get, right?
Yeah.
Everybody got that? Okay. Let's get rid of this for a second. I have some function. I plug in a 1. What pops out? F of 1. We don't care what it actually is. It's just f of 1. So what I'm going to do is say, okay, I want a point that's very, 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 very close to 1. In fact, I would like this point right here. I'm exaggerating this. We're going to imagine that we've just zoomed in really, really, really far here. Okay? Like here, you had a discrete set of points that looked like this. Okay? And so when we're trying to estimate this one, you said, well, grab the nearest one, right? That makes sense. What we're imagining now is that we've zoomed in really, 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 really far, right? And that we could do this. And every time you zoom in, there's a bunch of points. And so what you keep doing is zooming in. Really, really. Everybody get what I'm saying here? And we could pretend that we have an infinitely many points. Unlike in the real world where we only have a finite set of data, we're imagining that we could zoom in infinitely far here. And we're going to stop zooming for a second and say, before we go all the way to zooming into infinity, whatever that means, we're going to stop and say, okay, you're at 1 and you go some distance beyond 1. We're going to call that distance, whatever that distance is, we're going to call it h. Okay? So if you were at 1 and you went this direction by h, where are you now?
1 plus h.
1 plus h. That's the number that you would be at. And maybe h is like, 0.00000000001, right? It's a really, really, really tiny number. And wherever you are, and then if you were at 1 and now 1 plus h would be the number 1.000000001, right? So very, 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 very close to 1. Yeah? Okay. Okay, now. So I plug in my 1 plus h, and what do I get out?
F of 1 plus
F of 1 plus h, whatever it happens to be, and we can figure that out. Now what I'm going to do is say, okay, I'm going to estimate the slope, assuming that h is very, 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 very small. So, what is the slope of this line right here? How do I find the rise?
What's it be f of 1 plus h over f of no, f of 1 plus h plus f minus
f of 1. Right? Same way we did when we had 300 as an output minus the initial, which was 120, right? That's what you're doing. You're just taking the height. That rise is whatever that output is minus whatever that output is. Now what's my run? It's h, but let's be really explicit here. What we do is we go 1 plus h minus 1, right? The farther, but the same way you take the last point minus off the first point. You take the last point minus off the first point. But 1 plus h minus 1 is just h, yeah? Okay, so the slope that we care about then, which would be the speed, would be whatever we get when we plug in a 1 plus h minus off whatever we get when we plug in a 1 and divide that by h. So let's actually do that and see what happens. What is f of 1 plus h?
15.
1 times 1 plus h squared plus 120.
1 plus h squared plus 120. And then I take that and subtract off. Notice when I'm subtracting things off, I've used parentheses. This is, you've been seeing me do this for like 2 years now.
Minus 120.
Right. Minus what?
120.
Well,
No,
yeah,
one
but how about 15, 1? I want to be really explicit here, like this. Right? Plugging in a 1 gives me that?
Yeah.
Okay? All right. So let's multiply this out. What do I get when I multiply that back?
Squared plus 2h plus 1.
Yeah, so 1, 2h, h squared. H squared plus 2h plus 1 is what you said.
Yeah.
Yeah? Yeah, okay. Minus, so now I'm going to distribute this guy over here. Minus 15 minus the 120. Okay?
Yes.
Okay. All right. Now let's distribute that 15. I get 15 plus 30h plus
15h squared.
15h squared plus 120 minus 15 minus 120. Is there anything I could cancel out up there?
You can add all of our numbers
all
together.
all the just
120
numbers.
minus 135 plus 15.
Yeah, or how about this? What I'm saying is, can I cancel these guys?
Yes,
Yeah.
yes.
Yeah, that's gonna pay attention to that. There's a lot. Often with what we're gonna be doing in calculus, there's so often things are gonna
Oh, and the
cancel out.
120.
And the 120. That's nice. It's almost as though it didn't matter when we're trying to find the speed. It's almost as though it didn't matter where we started off. It's almost as though when we go to find out what the speed is, we're gonna lose that information. It's almost as if It's the only information we're not going to have. Anyway. Did you catch what I was saying there? I mean, like, you see I was connecting that back to something I said earlier, right? Like, the record of the speed has all of the information in it except for where you started. And it's funny how that just disappears. Anyway. Okay, now what do? I want to simplify this as much as possible because I want to know, I asked you, hey, what's your speed at time 1? And you say 30h plus 15h squared. Is there a way I can make this a little bit nicer?
Factor out of 15? Factor out of 15
and an
8.
8.
I can factor out of, okay, 15h
H
2
plus h.
or 2 plus H. Yeah.
plus h over h. Does something else cancel?
What was that? H cancels.
H
Yeah,
cancels.
h is-
And so I get
30 plus
15 times 2 plus h, or how about 30 plus 15h? And so, okay, the question was, what was my speed at 1? And the thing, remember what I said, this is a continuous function. We'll give a definition of what continuous means. But basically, we could zoom in as far as we want. We can make h as small as we want. And so if h were 0.000000001, this would be negligible, wouldn't it?
But
Yeah.
H can't be 0.
Now it can. We've canceled it out, haven't we? If I just plugged in an h equals 0, and this is something, I'm glad you said that, because this is something to note. If I just tried to plug in h equals 0, I would have f of 1 minus f of 1 divided by 0, which would be 0 over 0, which is junk, right?
Yeah.
And so that doesn't make any sense to do that. But what I can do is say, you know, it's kind of like if I had a function like this. If I had, let's say, x plus 1 times x minus 1 over x plus 1.
Oh, you showed us this one.
Right? I could say, you know what? This function is exactly the same thing as just x minus 1.
But one is undefinable.
1 would be undefinable if you just tried to plug it in,
Yeah.
right? But I could say, you know what? Or negative 1 would
Negative.
be. Negative 1 would be. But I could say, well, what happens when you get really, really close to negative 1? It looks like this thing would get close to negative 2. Right? Plug in a negative 1 for x. You should get a negative 2. But the thing is, like, yeah, if I cancel that stuff out, and we are able to cancel out the problem thing. And it makes sense. Like, you think, well, if you just plug in a 0, you're dividing by 0. It should, like, blow up to infinity. But does it make sense that doing this would make this blow up to infinity?
No.
Right? Like, as I bring, because you're imagining that you have a dot here and a dot here, and you have some line going between these two dots. And as I bring them closer together, the slope is just 1 divided by that, right? The top, that divided by that. And, like, that's not blowing up as I do this. It makes sense that it should converge to some finite value for a slope, right? That's what this is reflecting here. If I couldn't get rid of that h there, that would tell me that the function that I'm working with actually does blow up. Okay, like as that were to happen, or something crazy is happening. But when this can happen, you say, well, this actually does make sense, right?
Yeah.
Doesn't it? Like, I could make h really, really, really small and get that closer and closer and closer. And it's kind of like the same thing here. It's like, well, yeah, if that's always the same as that, you're not really in risk of dividing by 0 because those things are always going to cancel out. It's the same thing that's going on here. Because this guy is canceling him out, as he gets to 0, he's going to 0 at the same rate. And what does that do? Well, it gives you this right here. And so now we can say, well, now let's just pretend that this were like, you know, that h were 0.000000001, right? Well, then this thing is going to go to 0, the closer that you make that to 0. And so we could say it really looks like this slope right here should be about 30, which is what you said, wasn't it? Earlier, like, well, if you're going, if it takes you 2 hours to get to 60 and you're accelerating at a constant rate, then it should take you 1 hour to get to 30. Yes, you're right. Okay? Like, yes. But you could see that's not really the point here, is figuring out this specific problem. The problem is, given a continuous function, how can we estimate the slope of the tangent line at a given point? Okay? That's called the tangent line problem. Okay? And it's central to what we're going to be doing in calculus. So now that we've done this, okay, now, so that's Noah. That's what Noah did. And he figured out, okay, at time equals 1, I was going about 30. Man, took a lot to do that, but that's what he got. He found, okay, doing that. That's cool. Victor, on the other hand, also had a continuous readout, but only this time it was just of the speed. Okay, and so the speed at time 0, you were going 0, and it took you 2 hours to get up to 60. And it was constant, okay? And then you level off at 60, right here. Yeah. So, same question, how far did you go? Noah, how far did you go? How are you going to figure out how far you went?
Just wait.
How do we find, because we know that it's your displacement.
So 300 or whatever that was.
But what is it? How do we
Yeah,
find
300.
it? How do you know it's
We don't-
300?
No, it wouldn't be less because we
It would be less.
didn't start immediately.
You
at
weren't
60.
going 60. Yeah, you weren't going 60 the whole time. How could you now forget about the problem? I've given you a function. How do you find that right there?
Plug in a 3.
Plug in a 3. There we go. Okay. So total distance. Remember this. We take your final time minus your initial, right?
Yeah.
Plug in your 3, and you get 15 3 squared plus 120 minus, we know what the initial was 120, right? 15, or 3 squared is 9,
Yeah.
times 15 is 135.
Yeah.
Now, wasn't that what we said, right? 135?
Yes, we did.
We said that happened somewhere. Oh, and then
When you
plus
plug in a
120.
it's 135.
But then minus 1.
Minus 120, so 135. Okay, so, that's weird. It just happens to be the same as what you get when you plugged in a 1.
Yeah.
Sorry, I didn't want that to happen. So that should be, what, 135 is what we said?
Yeah.
120 minus 1, so that's 135 plus 120 minus 120 is indeed 135. So that's the total distance that you went. Hey Pete, could you keep it down, please, buddy? We're still trying to learn here.
The function wasn't like exact because
Yeah, well, I derived this using methods that we will learn soon. So yeah. So okay, and speed at time equals 1, we found was 30, right? Miles per hour. Okay, now here is obviously a line, and you already did this in your head. You know that halfway between that line was halfway between these points, and so you said that's 30. So here we go. Speed at t equals 1 was
30.
30, right? So this is your g of t, and it turns out to be what, 60 over 2, so 30t, something like that. And then for the first
60.
part, and then just 60, so this is when t was between 0 and 2, and this is when t was beyond 2, right? Piecewise function, everybody comfortable with that?
Yes.
That's what that is, right? It's this line from there to there, and then it's that line from there to there.
yeah.
What's the total distance that you traveled?
No, we take this slope of the first line and
Like the length.
Victor doesn't have this information. Victor doesn't have this information. Now, how did we do this?
Oh, we can take the slope because we have 2 lines. You can take the slope of 12 and like add them or something.
Or the area.
Area. And now I haven't proved this. We will prove this in this class. That yes, the area here is going to be the displacement.
Oh, there's
over
a
here.
triangle we could use.
Yeah, I
triangle.
like that. So let's do that. So let's do the triangle first. The triangle's what? What's its height?
30. No, 3. Wait. 30 of...
60.
Oh, 60. Yeah.
And what's its
60
base?
Times 2 divided by 2.
So 1/2 times
1.
2 times 60,
Which is
just 60. So we have 60 here. And that's 60 what's? Sandwiches per milligram?
miles per hour. Wait.
Well,
Wait.
miles.
Yeah.
Right? Yeah, I shouldn't have said per anything. Because you took hours multiplied by miles per hour and you got miles. So that's 60 miles. Now what's this block?
1
right there?
times 60.
1 times 60, which is another...
Wait, that's not 135.
Uh-oh. Oh, I probably did this wrong, guys. I'm sorry. I thought I figured this out last night. Boy, really sorry about that. I did something wrong there. I'll figure it out and we'll rectify it next time. Oh. What did I do, dude? 120, 130. Okay, did we do this right? Plug in your 3. Did we do this right? What's 3? 15 times 9. 9 times 5 is 45.
Plus
9 is 135. Is that right?
Yeah.
9 times-
Yes, 135.
I don't know what I did wrong, guys. I'm sorry. That's... Oh, wait. I'm really sorry about that. I don't know how that got by me. I'm not sure what I did wrong. What is your displacement? 135 plus 120 minus 120. Darn it. Oh, this is going to drive me crazy.
Or do we get to minus 120?
The displacement, right? Your final was whatever 135 plus 120 is, which is 255. So then your displacement was 255 minus 120, 135. Oh man, that's so annoying. Are we sure this is 60? 60? Well, you know what? I might have messed something here up. In fact, let me see. 60 and 1 and 30 comes down to
It's not working.
15 comes down. Oh! Constant! This is assuming this thing.
Oh, yeah.
Yeah, no, I'm sorry. We would have to, that's what happened. We're assuming this thing right here. Everybody get that?
Yeah.
We're not taking into account that now there's a new function right here. I didn't write this as a piecewise function, which I should have written as a piecewise function, which would have required more work that I didn't want to do. So, I'm sorry. In fact, on my notes, I didn't bother to do this side of it because of how complicated this becomes, because now we have to find, okay, given that point, we know that the slope is 60, we'd have to, well, I guess we could, let's just for my pride, I'm sorry, I have to do this. This line right here has a slope of 60, so it's 60t plus b. Now, we know that when you plug in a 2, now this is where we get that. Plug in a 2 and what pops out? F of 2 is 15 times 2 squared plus 120, which is 15 times 4, which is 60 plus 120,
So 180.
which is 180. So we know that this is 180. So when we plug in a 2, we get out a 180.
180.
So 180 equals
120.
60 times 2 plus b.
Which is 60 equals 60.
180 equals
120.
120.
120 plus b, so b equals, what did you say?
60.
60, yes. So here's the second part of this guy. 60t plus
60.
60 whenever t is bigger than 2. And so now to find this output value, this will be so worth it. I'm sorry, Sarah, it's going to be so worth it.
Okay.
Now we plug in a 3, and we get 60 times 3 plus 60 is my output. 60 times 3 was 180.
Yeah, 60 is 240.
Plus 60 is what?
240.
240. So now my final position is 240. You see how Noah had to do a ton of work here? Oh man. Okay. So 240 minus 120 is your total displacement. 240 minus 120 is what?
120. Yes. Which is what we got.
Ah! Sorry about that. I should have looked at my notes more carefully because I was going to say, and I even have it there, like, don't try to do this over here. Trust me that this is how far you went, because doing it over here is way harder. I completely didn't see my note. I'm sorry. But anyway, you see how all this stuff is connected?
Yes. Yeah.
That's the point of all this. It turns out the fundamental theorem of calculus, which, believe it or not, is what we're going to build up to throughout the whole thing, is connecting these two ideas. If you have a record of how a function changes, that's the same thing as having the area of that record, right? That these things are connected in this way. That is what this is. The only thing you don't know is, hey, where did you start? So sorry about that, guys.